This is CPE 233 Experiment 1, and what we're going to talk about is Part H of Experiment 1. So there's many parts to it. You're only required to do Part H. So Part H has to do with reading values from a ROM, doing something with those values, and storing those values in a RAM. And then after it's all stored, it displays those values. So what's going to happen here is you're going to press a button, and when you press that button, it's going to read a single value from two different ROMs. It's going to take the average of those values. If that value is greater than 15, it's going to store it in the RAM. Otherwise, it's not going to store it in the RAM, and it's going to go on to the next value. And so the issue here is that you're going to have to display two different things on the 7-segment display. One of the things is going to be the value stored in the RAM, which is this one right here. And the other thing is you've got to store the final count of values, of valid values in the RAM. Now what you're going to see is the valid value count is constant after you do all the calculations, whereas the values in the RAM are going to be continually displayed, meaning it's going to display one value, go on to the next value. That's going to do that continually. So the constraints in this is that I only want you to use standard digital modules. Don't use big magic circuits. And the issue is that you can use magic circuits, but you can't do that on an exam. And so I want to get you used to using standard digital modules when you're designing your circuits, not a magic circuit. It's not a class in Verilog. It's a class in digital design. I want to see you do actual digital designs. So this, once again, this would be pretty easy to do with using mathematical operators, but I'm going to ask you not to use them. And now I think you'll see that it's really easy, calls out for the use of a mathematical operator in one place. And if you know what I'm talking about, then you can do that. But I don't want to see tons of stuff in here. But so if you can, my opinion is you can get away with using one mathematical operator, and that's it. Otherwise, not a big deal. You can just use an extra ripple carry adder in there. So the issue here is that the state machine is going to control the circuit. Don't use any more than 6 states in the state machine. Make sure that state machine is completely independent of the RAM and ROM size in this experiment. So these state machines have storage, and the state variables are the only memory in the state machine, and I want to keep it that way. Don't try to put a counter inside the state machine or anything weird like that. Also, don't input data into the state machine either. The only thing that should be imported into the state machine is your status values. You know, the non-status values such as data, you don't want to do that. And also there's, this is just a brief description. There's a lot more descriptions inside the experiment. By all means, go look at that. So there's lots of provided modules on Canvas. Don't write new ones. Use the provided modules. All the modules except for the FSM template has an instantiation template in it. So by all means, cut and paste the instantiation template into your top level. Do not change the modules themselves. Essentially, what I want you to do is override the default values, and then if you don't know how to do that, it's kind of indicated in the instantiation template, which is in the header of the modules, and it's commented out, and you'll get an idea how to do that. Or you can just ask me or ask someone. So when you're hooking this up, you're not going to have to use all inputs or outputs, but the idea here is all the inputs should be assigned. If you're not using it in your experiment, it still needs to be assigned. Give it a non-damaging value, whether it be 1 or 0. And the outputs, you don't have to assign outputs. You can leave them hanging. So once again, lots of modules out there. The muxes, registers, counters, ripple carry adders are out there. As far as memory goes, there's a generic a RAM out there, use that. There's also 2 ROMs out there, and associated with those ROMs are 2 .mem files. Now the ROM, each ROM reads from a given .mem file. It's kind of hard-coded. It's kind of funky, but that's just the way we're going to do it. There is a finite state machine template module out there. I want you to use that also. There's no instantiation template in there. You're expected to do a lot of modifications to it. And there is a universal 7-segment display module that you should use. The idea here is I don't really know how it works until I read the directions in the header, and it tells me everything I need to know about it. So by all means, look at the header of that thing. The approach you should take is generally a top-down approach. First, you should understand the problem, and the problems generally call out for modules in your circuit, such as, if you have to make a decision, it's generally a MUX. If you have to store values, it's generally some type of register. If you have to count something, wow, it's a counter, etc., etc. So once you plop those modules down, connect it up, connect the modules, which includes the data, control, and status lines. And after that point, you're going to design a state diagram that models the finite state machine. Once you get that, translate the state diagram to a Verilog model and drop that in your circuit. So the idea here is understand the problem, design it on paper first, keep it simple, don't be clever. Realize that the design process is iterative, meaning you're going to make mistakes at various parts of the process. No big deal. Just go back and fix them. Don't expect to get it right the first time. You can expect to debug either visually or on the board, or visually on the board or with the simulator. Essentially, once you get everything designed, you're going to translate it to Verilog, and you're going to test the design. Now, if you're lucky, you don't have to use the simulator. You can just do all the testing on the Basis 3 board. But certainly along the way, ask a lot of questions, send me diagrams. Let me help you along the way. You're not on your own in this one. This is the top level module. What you can see here is a button and a clock input. The clock just runs everything. The button is kind of the go signal for this circuit. The circuit does have 4 LED outputs, which we're going to use as which is going to indicate the RAM address. And segments and anodes are used to drive the 7-segment display. And that is it, folks. Oh, well, one is due. It's due 6 class meetings from the day it's assigned, which is going to be assigned the first day of class.